Et donc, merci beaucoup d'être venu. So, yes, so many of you know much more than I do on certain of the topics I will treat. So that's the challenge of talking about research as it's being done. And so I hope that you interrupt me or correct me if I say some things that are incorrect. So my plan today is to talk about methods. I think that despite what some famous physicists say, in the last 20 or 30 years, there's been lots of progress on treating the problem of strong correlations. And I won't quote any. So, obviously they are not perfect, otherwise the problem would be solved, but I think that they have been benchmarked and we know when they fail and we know when we can expect only qualitative results instead of quantitative ones. And I think that it was very much motivated by high temperature superconductivity, but now we are realizing that there are some broader applications like those that are being done here at the Collège de France on real materials. So perhaps in the long run, what will survive is the application of these methods to materials. So in the first, as usual, my talk will be divided in two parts. In the first part, I'm going to talk about quantum cluster methods, which means cluster perturbation theory, and cellular dynamical mean field theory, and the dynamical cluster approximations, which are the best known of these methods, but also variational cluster approximation within the context of self-energy functional. So in this first part, I will talk about all the methods, and I won't be very rigorous in the way I derive them, but I will try to show you that some benchmarks. And it's not so interesting to look at benchmarks and go through an exhaustive list. So the list won't be exhaustive, but there will be a few pointers in the transparency. So if you wish to go more in depth, then you can do it. Here you will have sort of a broad view of what type of test has been done and where it's applicable and so on. And I will end this first part by a remark on other materials. During this series of lectures, I've talked a lot about high-temperature superconductors, but I want to show that it applies to other materials as well. So it will be organics and heavy fermions. And in the second part, I will talk about impurity solvers, which are at the heart of the success of these methods. I will do some advertising for maximum entropy analytic continuation, and I will end on the board with some formal considerations with self-energy functional and how you can derive DMFT from this. So it's based on some reviews. I will inspire myself mostly of what we have done a long time ago with some more modern things. And if you're ever interested in looking at this reference, I suggest that you look at the ConMat version that is in color and so on. And somehow everything came out black and white, and some of the curved figures are destroyed in this published version. So cluster perturbation theory. So the idea is to partition the infinite system into finite clusters, and there are many ways to do this. So when I draw this picture here, I mean something like this. You treat a cluster here, and this bond here is added later on. So in cluster perturbation theory is sort of like the Hubbard-1 approximation for a cluster. So what that means is that we divide the hopping into two pieces. So to describe an atom, once you've partitioned the system, you need to specify where it is within the cluster. So that's mu nu. And you need to specify which cluster. So that's mn. So this has two pieces, a piece that lives purely within the cluster, so delta mn, and a piece where you hop between the different the rest of hopping between the clusters. So the Hubbard-1 approximation is just that the Green's function is the Green's function in the cluster or the inverse Green's function, I'm sorry, is the inverse Green's function in the cluster minus the hopping between clusters. So it's like first order perturbation theory in little t. It's sort of the simplest thing you can think of. And the cluster Green's function here is just what you would calculate by solving the cluster. So there's a self-energy. Now you notice that this piece here of the cluster Green's function combined with this piece means that you have the whole hopping. So it's like G0 minus 1 for the whole cluster. So there's a way to rewrite this expression using the Green's function for the full lattice like this. So these two expressions are identical. This is a matrix notation. That's why there's the hat here and the hat there. Here I just looked at specific matrix element. But it looks at, it inspires you of another way to look at the problem, which is to say that the lattice Green's function is the non-interacting one minus the cluster one. And so it's like saying that the self-energy computed on cluster is the same as the self-energy for the infinite system. In single-site dynamical mean field theory, this is just not a matrix. This is just the frequency-dependent object. But in general here, it will depend on cluster. So the first issue that jumps at your face, that is, well, okay, I forgot to mention that it's exact in t equals 0 and u equals 0. First issue that comes up to you is the periodization, which we rarely talk about. If we start from this cluster that has been partitioned, then the original wave vector for the full lattice can be decomposed in two pieces. A wave vector that is on the super lattice, if you want, that describes the Fourier transform for the translationally invariant system that goes from one cluster to the other. And K is the Fourier transform associated, the Fourier variable associated to one cluster. So here for this example, there are 4 values that this big K can take. And K tilde runs over a quarter of the full original Brillouin zone. So all the information is in this Green's function that depends on K tilde plus K and K tilde plus K prime. It's not going to be diagonal in big K and big K prime, but it's going to be diagonal in K tilde because K tilde is hopping between clusters. Is that clear? Because it's sort of a simple step, but sort of, I mean, in other words, there are indices mu nu, and we need as many wave vectors as there are indices mu nu. So it's not diagonal in K and K prime, but suppose I want to compute the total number of particles. Then I'm instructed that I should take the trace. So usually, so it means that we take K prime equals K. So usually with these methods, when we draw spectral function, we draw just the diagonal piece of this quantity. So we take K prime equals K, and now there's K tilde plus K, so we write G of K. So that's what is called periodization. And that's how you get these Fermi surface plots, these momentum distribution curves. That's for hole dope, electron dope, using these cluster methods for a cluster of size 8 here. And you see that, like in experiment, you have these hotspots for the hole dope and for the electron dope. So what are benchmarks for, yes, Olivier? The worst thing you can do is periodize the self-energy. Because if you do this, you find that there are states in the gap at half filling. And I will come back on this. So here's, again, I won't spend much time on benchmarks, but just to show you that if you have an exact diagonalization solver, this simple cluster perturbation theory is already a big step towards the right answer. Take the 1D Hubbard model. This is the result of exact diagonalization for 4, 8, 12 sites for u equals 16. And the same thing with cluster perturbation theory. which the hard work is doing the exact analyzation. Cluster perturbation theory is trivial. But you see that already for 12 sites, you get the spectrum that you expect for the 1D Hubbard model. Again, this is a little bit of a mess. I won't go into all details, but I just want to show that for 12-site cluster perturbation theory, the relative error compared with beta and zats here that is plotted as a function of hopping t at fixed u is fraction of a %, whereas if you take the exact analyzation result directly without this strong clustering perturbation theory, it is much, much, much bigger. Okay, now if we want to go beyond this simple cluster perturbation theory, we based on a very extremization problem that's self-energy functional theory. So I will explain in the second half the details, but in picture, the point is that there is a function or a functional of the self-energy that is at extremum at the optimal solution. So what we do in the dynamical mean field theory or on all these cluster methods is to modify the one-body part of the Hamiltonian in such a way that, so let's say T prime is this modified one-body Hamiltonian, right? So for example, we cut all the bonds that connect the cluster to the rest, and we treat that with a bat. So that's what I mean by a modified one-body Hamiltonian. And that allows us to vary the self-energy, okay? But in a subspace of all possible self-energy. So we don't find a true extremum, but we find an extremum which, the larger the space here, the closer it will be to the real answer. So there are three different types of approximation to this self-energy functional. One is to approximate the equation for the extremum. That's the Euler equation. So that like treating it in Hartree-Fock or something. The other one is to write an approximate functional. So for example, you take a finite set of diagrams or some other methods. And in density functional theory, that's what you have. You have an exact functional, and you treat an approximation for that functional. The third set of approximation, which is done here, is to take, I don't know where there's an and here, the exact functional, but for a limited set of possible functions. That's what I described in the previous transparency. And that will be clearer later. So in other words, this functional will look like this. It will have the functional that is universal here, which means what we mean is independent of the one-body part of the Hamiltonian. And the one-body Hamiltonian enters only in G0 here. So the idea is to take for f of sigma here the exact result for a problem with a different one-body Hamiltonian. So if you take this one-body Hamiltonian where I cut all the bonds that connect the cluster to the rest of the system and I replace by a bat or whatever, I can compute this f of epsilon just at the difference between left and right-hand side. So you see the prime here means that I have my different one-body Hamiltonian. But it's exact within this limited set. And now you vary with respect to the parameters by varying h0 of t prime, and you look for your solution. So that's the idea of this self-energy functional theory. Now let's go beyond cluster perturbation theory. It's called variational cluster perturbation theory. So the idea there is, suppose you have some broken symmetry. Clearly, I cannot treat it with cluster perturbation theory because within a cluster, I'll never break the symmetry. So what you do is you add to the Hamiltonian a symmetry breaking field. So this delta here would be, for example, an alternating up-down field for an antiferromagnet. But because you have added it to within the cluster, you don't do any mean field factorization within the cluster. You just add this Weiss field. Then you subtract it in the in this term that is treated perturbatively usually. So if you do this, you get the exact result in the non-interacting case. But here, in the presence of interaction, the result will depend on the Weiss field H here. That is, I should have written it here, but that's the thing that couples to that's the alternating field. So you optimize with this function that I drew. That's a technical detail. Here you have some explicit function that you need to minimize with respect to these Weiss fields. So let's see how this does, some consistency checks. So this is a problem that was treated by my colleague, David Sénéchal, where we have the triangular, the Hubbard model on the triangular lattice. If you take these two clusters that you couple by just cluster perturbation theory, then you can tile the whole infinite lattice and use this as your basic cluster. Again, I won't go to details, but I want to point out just one very simple thing, is that here they were able to look at clusters that were larger and larger, and they looked at different values of U, and the point is that they looked at the value of the Weiss field as a function of the size of the cluster, which is here measured just as the fraction of sites in the cluster compared with the fraction of sites that should be there in the infinite cluster. In other words, you remove the boundary sites. And the point that is nice is that you see that the Weiss field goes to 0 as you increase your cluster. That's what you want, right? In the infinite size limit, you want the broken symmetry without any Weiss field. That's another measure. So again, these are about comparing ground state energies as a function of U. The message there is just that you do, this is for the F filling, the 2D Hubbard model, you do exact diagonalization, you get a much worse energy than you get very simply by variation cluster perturbation theory or by quantum that you can compare with quantum Monte Carlo as a benchmark. Okay, now I move to cellular dynamical mean field theory. This is then the only thing we're left with is the dynamical cluster approximation. So there are many ways to derive single-site dynamical mean field theory that are well explained in the review by Antoine, Gabi, and Marcello Rosenberg. There's a cavity method. You can use the local nurture of perturbation theory in infinite dimensions, so you can control with infinite dimension. Expand around the atomic limit. You can use ideas of effective medium theory, do local approximation for Luttinger-Ward, or there's this Potov self-energy functional that I already talked about and that I will use later on in the second half. So all these methods basically give you the same set of equation, which I've already described, where you solve, in the case of DMFT, one impurity in a bat. You compute a self-energy, you put it in the infinite lattice, and you see if, when you project the infinite lattice on the impurity, whether you get the same Green's function. If you don't, you modify the bat until you get the same result. So from this point of view, you can go from single-site dynamical mean field theory to cluster by replacing the infinite cluster just by bats. The dynamical cluster approximation that I will describe later is based on a rotationally invariant version of the same thing. Okay, now there's one concept I need to introduce, which is the hybridization function. So suppose I have a cluster, and the Hamiltonian for the cluster here, without the interaction, is just replaced, is just this, I write like a T here. I should have written plus T here, I'm sorry, that's an error. Omega minus big T. And then the bat here are represented by these energies. So these are big matrices. Think of exact angles. Here it would be If it's a 4-site, it would be just 4 by 4. But here, if I have an infinite number of, that would be an infinite size matrix. But I can work just in this cluster coordinates just by solving, inverting this equation for the Green's function that lives on the cluster only. Then all the rest of the bat here is represented just by this function that we call the hybridization function. And the only place the interaction will come in, if I put it just on the cluster, is in the self-energy of the impurity. It will enter nowhere else. So the self-consistency can be expressed as follows. If I can compute the impurity Green's function on the cluster, I can extract a self-energy by using this expression, where the G0 impurity to the -1 depends on the hybridization function. That's what I just wrote. Now, the projection I talked about means that thinking of this as matrices, I integrate over K tilde, that was this related to this translationally invariant contribution. And that gives me something that lives only on the impurity, and it should be equal to the impurity Green's function. If it's not, I modify the hybridization function until this equality is satisfied. Okay, so that's another way to look again at the same thing. So this is repeating the same thing. I obtain the Green's function for the impurity in a bat. So the G0 will contain this hybridization function. I extract the self-energy, substitute the self-energy in the lattice Green's function, project the lattice Green's functions on the impurity. If the two Green's functions are unequal, I multiply the bat until they are equal. Positive aspect is that long-range order comes in naturally. You can allow symmetry breaking in the bat. The short-range dynamical and spatial correlations are included exactly, but you miss the long wavelength particle hole and particle-particle fluctuations. Benchmarks. So here's a paper that was written here in Paris, in a great part, where Marcello and Antoine are in this paper. So you look at the different cluster size. That's the corresponding in momentum space that correspond to what you were doing here. And you plot, for example, the imaginary part of the self-energy for a very small doping here. It's been done for many other doping. For a temperature that is 0.06 little t, a U that's relatively large, 8, and even some T prime for these small doping. The temperature here is still a little bit, well, it's still on the high temperature side in some ways, but you sort of start to enter the pseudo gap regime. And the point is that 4-site, which is this result here, is comparable to 16-site, which is this result. And that you have convergence is faster at certain points. Now, in the case of this paper, and coming back to the question of Olivier, they looked at different periodization schemes, and the one they prefer is to periodize exactly in the same way as I mentioned for the Green's function, but not the Green's function, but the cumulant. And what is meant by cumulant is, well, is basically the Green's function, but that is irreducible with respect to all terms that take you from one side to the other. In other words, once you periodize this, then the Green's function is just this, you see. Think that if this was translationally invariant, you would just invert this, and that indeed would be the inverse of the Green's functions. But I think there are not that many differences between periodizing the Green's function and the cumulants. and the results are pretty good. But the self-energy, periodizing the self-energy is bad for the reasons I said, namely, well, if you're far from half filling, it's not a, if you're not, I'm sorry, if you're the coupling is not too strong, or if you're far from half filling, it's okay. But otherwise, you get states in the Mott gap, which are clearly unphysical. The last approximation is the dynamical cluster approximation. So, yes?
What is exactly the statement comparison? I mean, you can, of course, sort of speak 16 sites and 8 sites, then compute this periodized, and then one compares what?
Yeah, well, you compare, I showed, it's really comparing, looking at the convergence as a function of system size. So they look of the same thing, though.
You cumulate periodize, and then you equate
Yes.
the self-energy, and that is what is plotted.
Yes. So dynamical cluster approximation is this. How do we go to, how do we build a cluster that is invariant under translation? Well, okay, first of all, this dynamical cluster approximation cannot be derived from a self-energy functional, as far as I know. And it's based on mapping on a translationally invariant cluster. The way this is done, I can explain roughly in this way. Take the hopping, so Mn is between different clusters. Mu nu is within a cluster. And you see that you have this double Fourier transform. Okay, so Rmn is the distance, or tilde mn is the distance between the clusters, and big R is the distance R within the cluster. So it will, in the translationally invariant system, it depends only on these, the sum of these differences. So I can start from the original translationally invariant hopping and go to local terms this way. So it's just Fourier transforms, nothing fancy. What we do in cluster dynamical mean field theory is we just focus on a cluster. So one way to do this is to say, okay, if you take this and you sum, you just do the sum over big K, and use the fact that K dot Rmn, which is the distance between cluster, is 0 modulo 2 pi, you see that you get a hopping that depends on the sites within the cluster, and that depends on K tilde, which is this reduced Brillouin zone that goes everywhere. So in this, there's no approximation, just a way to do this. Now suppose I did the same with Mn instead of mu nu. Then I would sum over, so the sum over K tilde, and the same function. But now you see, it will depend on Mn, and we want something that is somehow periodic. So the way they do it in DCA is to drop this phase factor here, the K tilde dot Rmn. And then in DCA, the kinetic energy also depends only on big K. So the self-consistency that in cluster dynamical mean field theory meant inverting this matrix, summing over K tilde and seeing if it's equal to the cluster Green's function. In the case of this DC dynamical cluster approximation, is reduced to a scalar equation. So for every big K, so every patch in momentum space, we have this self-consistency equation. One way to formulate this DCA is to say that you agree not to conserve momentum perfectly in these diagrams, but just within patches. So a benchmark that was done also in good part here was to tile momentum space in different ways. So with 2 patches, 4 patches, 8 and 16 patches. And here is four patches, just like here, but sort of you use your inspiration and you think this is going to be better because you're going to take into account the pi over 2 point better. So the tests were done in a comparable temperature range, T equal 0.05, U equals 7, some comparable T prime as the tests were done with cluster dynamical mean field theory with many dopings. And the conclusion was that as long as you take this patching for foresight instead of this, you get the general picture that there's this momentum space differentiation as you move close to half filling, and no momentum space differentiation far from half filling is cluster independent. Also here there's another feature in this case, which is called MUT selective, sector selective MUT transition. So, one of these patches will become gapped, just like in a MUT insulator. That's something that does not happen in cluster dynamical mean field theory, but in this method is a way to represent the pseudo gap. So now let me finish this section by comparing the various methods, the single site, cluster, and DCA. And we take inspiration from this paper of Antoine that says that to think locally, you have to start from high temperature and high energy. So here with the 3D Hubbard model, they compared with the high temperature series expansion. And the final conclusion is that as long as the temperature is of order 1 in units of hopping, you basically get the perfect agreement. Now here's another set of comparison. Again, I won't have time to go through all details, but this is done at smaller coupling, U equals 40. And this line is for the triangular lattice, so you can forget it. But all the other lines are for the square lattice using single site, DMFT, 8x8, 4x4, all sorts of sizes. And this is the reference. So this was done by Quantum Monte Carlo with quite big system sizes and extrapolation to the infinite size limit. So this is double occupancy as a function of 1 over temperature. So low temperature is on this side. Again, at high temperature, for temperature of order 1, whatever you do, you get the right answer. Otherwise, there are divergences. It's not the same. And the point is that you get a few percent discrepancy. One thing that's missing from all the cluster methods is that in the infinite size limit, the double occupancy, as you go low in temperature, which is to the right, double occupancy increases at some point. And the reason no, I'm sorry, this is not double occupancy. Sorry, all wrong. That's square Z, so it's 1 minus twice double occupancy. So the reason this goes up is because double occupancy goes down. The reason it goes down is because you're trying to form an antiferromagnet. So SZ squared goes up. So to test methods that want to include the long wavelength fluctuation, you need to improve all these cluster methods to see this effect. This is all half filling, I should have specified. Well, it's a square lattice, so TNL is at 0 temperature, but the crossover to the renormalized classical regime, where the correlation length starts to grow exponentially, is precisely where you see this going up. Yes, Olivier? It's not. Yeah, it's not necessarily monotonic, effectively. Yes. Yeah, it should work well, but
I'm a bit surprised about this because as you increase the size of the cluster, you should be able to do better and better on capturing the short-range antiferromagnetic order, right?
yeah.
So at least the agreement should go better and better, lower T, and then at some point, collision end becomes too large for the cluster.
Well, if you look at DCA 8 by 8, it is the upper triangle. Well, it's a little bit complicated.
Yeah. We're looking at small differences here, of course.
Yeah. It's a little bit messy, and I must say it's been a long time since I looked at this, so I'm not sure we want to spend the time to look at all the details, and it's not so clear, right? Because it's the same symbols if it's the same method. The only difference is the color here. So it's, yes. Well, TPSC seems to be doing, yes, compared with this, somehow, I don't know why, but it didn't seem to be doing too well. It's good compared with DCA, but not that good compared with this at low temperature. Okay, but if you want to really see this agreement, then you just need to lower the temperature. Okay, so this is temperature, this is interaction strength U, and half filling on the square lattice. And here there's a CDMFT 2 by 2 is, there's a first order transition here, and there are lots of crossovers that I cannot describe in all detail, but lots of crossovers that start at the critical point. This is DCA 4 by 4, again with lots of crossover, and this is single site DMFT, again with lots of crossovers. So the point I want to make is that the onset of long range order in these mean field approximations, so it should not be there, but still is this curve, and the onset of the renormalized classical regime is here. So the point is that all the antiferromagnetic fluctuations are very big here. So you see, if you look at single site or CDMFT or DCA, there will be big differences. On the other hand, the qualitative results that are many crossovers are all the same. So if you're just interested in saying, okay, there are crossovers, and that's what what the lines will look at, you know, like here they go to the right, whether it's DCA or CDMFT, it's the same. So the only crossover that seems to be universal for all these methods is again at very high temperature, well, 0.2, 0.3, and it corresponds, so this crossover corresponds to the opening of a mud gap in the region where it's big enough that it starts to look, I'm sorry, as long as the chemical potential is in the gap, it starts to look as doping semiconductor by thermal fluctuation. Now, if I look at the CDMFT versus DCA for the 1D Hubbard model, this is the value of the Green's function as a function of 1 over the length of the system. The CDMFT are the open symbols, and DCA are the closed symbols. So the filled symbols from DCA, and this is just the Green's function evaluated at imaginary time equal beta over 2 at a point where the spectral function starts to develop a gap. In cluster dynamical mean field theory, you see this gap starting already for a size 2, and then you go to larger. And DCA, you have to go all the way to L equals 8. But the point is that the method for large U, here this is large U because U equals 4T is equal to the bandwidth. So for large U, in a strong correlation regime, at least if you look at quantities like this, they're pretty similar. if you go now in 2 dimensions, and for, again, the DCA are the black symbols and cluster are the open symbols. Then you start to see that the pseudo gap takes a very long time to appear. You need to go to big systems to start see anything that may look like a pseudo gap. Yeah.
I thought it was converging like 1 over x squared.
Perhaps, yeah. It's just
Just that we are not big enough size.
well, yeah. Here there's like 3 points only. Here we just put 1 over L because in CDMFT it was claimed that it goes like 1 over L. But yeah, that depends on the quantity. And in fact, that's my next remark.
If you look at the center or exactly, they are like a constant.
Yeah.
So
Yeah, so it is this slide actually. So by looking at large N models, for example, in other cases, it was shown that local quantities, like double occupancy, converge exponentially fast with CDMFT as long as you you stand in the center of the cluster, and otherwise 1 over L. And DCA is faster for long wavelength quantities. So it depends on the physical quantity you're interested in. Yeah. Well, already in cluster perturbation theory, you see these the single particle spectral weight as this thing, which is really the branch cut, except that it's rounded. But if you look at the plot, for example, of A of K and omega, and you're not too picky about resolution, you will see the spin-on and the hole-on branches. With relatively small system sizes. Okay, I've talked about the organics already. I want to just end with applying these methods to other systems like the heavy fermions, where you see temperature as a function of pressure. There's coexistence in these type of compounds between antiferromagnetic and supraconductivity in some region with an antiferromagnetic quantum critical point. So this is a model that was done by Wei Wu, who is here, so he will explain to you in detail on some other occasion. Here I just want to, it's almost just an advertisement for this model, is just to have F electron on the red sites and hybridization either on the same site, and the conduction band is these blue things here, hybridization both on the same site and on nearest neighbor site. So in this model, there's frustration. If V and V prime are either V or V prime are not 0, antiferromagnetism is frustrated. And then if you look at the phase diagram as a function of V prime, for a fixed ratio of the frustration, fixed ratio of V over V prime, so this is one calculation in orange, where you see you have antiferromagnetism and superconductivity with an antiferromagnetic critical point and coexistence in between. Now you change the ratio V over V prime, you put less frustration, so you have more antiferromagnetism, and you see that the maximum of the superconductivity follows the antiferromagnet. So again, so a quantum critical point here is related to the maximum in the superconductivity. Yes?
Do you have the coexistence? Or
Yes, yes. This region, I should have used another more recent plot that we have. This region here is really coexistence, is the two orders. So to close this first part of the lecture, I would say that as far as methods are concerned, the challenges for weak to intermediate coupling, the two-particle subconsistent approach that I described, is to generalize to broken symmetry states, to multiband systems and to be able to use in realistic calculations. At strong coupling, the challenge is to include long wavelength fluctuations, so in the vertex, like what Olivier and Thomas are doing, and to see if the feedback of these long wave fluctuations on double occupancy is observable. So we will stop for, let's say, 10 minutes.